Hi, I am Dr. Samir bin Osman, and in this video we'll talk about the principles of physics. So physics is the study of matter and energy, as well as their interactions and motions throughout space and throughout time. So at the very early instance of the initial expansion of the universe, which is called the Big Bang, emerged four fundamental forces, two of which are nuclear, i.e. in the nucleus of the atoms, and two are overarching. So let's talk with the nuclear ones, starting with the strong nuclear force. So the strong nuclear force basically is the force that holds the protons and neutrons together inside the nucleus. It is by far the strongest force in the universe, but only reaches as far as the width of a proton, so like very, very short distance of action. This binding energy is actually what gives mass to the nuclei, wherein lies 99% of the mass of the universe. So its release through either nuclear fission or nuclear fusion causes nuclear reactions and explosions. It is carried by particles called gluons, like a glue, because it glues nucleus components together. In contrast to that, we have the weak nuclear force, which is 10,000 times weaker than the strong force, and acts at ranges that are 1,000 times even smaller than the strong force. And it is responsible for the conversion of protons into neutrons and vice versa, along with the emission of beta radiation. As the early universe was like a sea of neutrons, converting most of them into protons allowed atoms to form and make the universe as we know it. The opposite conversion makes unstable atoms that have an excessive amount of neutrons obtain a more stable ratio of neutrons to protons. This force is carried by particles called W and Z bosons, and we will talk about this further along in other aspects in engineering, etc. The third force is the electromagnetic force, which is about 100 times weaker than the strong force, but has an infinite range, so it's not limited in its range, though it potentially exponentially diminishes with distance. It binds negatively charged electrons to positively charged atomic nuclei, and thus gives rise to the bonding between atoms to form molecules. It has no effect, that is perceptible on large objects, as it's unidirectional, and the charges within those objects tend to cancel each other because they're in all different directions, so some of them cancel each other out. This force is carried by the photons, the same photons that basically you see in light, but it's because light is also an electromagnetic force. The last fundamental force is gravity, which is by far the weaker force, which is 10 to the 39 times weaker than the strong force. But it has an infinite range, just like the electromagnetic force. Also, of course, exponentially decaying with distance. But contrary to the electromagnetic force, gravity acts on all particles regardless of their direction. So it's multi-directional, and therefore does not cancel out for larger objects. And the opposite, it actually amplifies in large objects. And that is why it is the dominant force for large objects at large distances. Now, how did these forces shape the universe as we know it? So the universe is made of matter and energy, which can be converted into each other. As the universe cooled after the Big Bang, the strong and weak force made neutrons, and then the weak force made protons. Then electromagnetic force pulled electrons to make the lightest possible atom, which is a proton around which an electron spins, and that's called the atom of hydrogen. So then hydrogen was clumped by gravity into masses that are so dense and so hot that they started performing nuclear fusion of two hydrogen atoms into helium, giving birth to the first stars. And then stars came of different sizes, some of them small, some of them large, some of them are giant. And those giant stars, at the end of their life, they compress very quickly and generate even more heat and more pressure, and so produce more atomic fusion, and then produce heavier atoms, just like such as carbon, oxygen, all the way to iron, etc. And then they explode right after into giant explosions called supernovae, and then disperse the new matter that they just created into outer space. So then this matter that's created, this gets condensed again by gravity to form planets. And so, and everything that's inside planets, including us. And so that means that we are practically made of stardust. Now, all the matter that I talked about and that we observe in this universe is only about 4% of the total mass and energy of the universe. It so happens that about 26%, about like a quarter of the matter energy of the universe, of the content of the universe, is made of an unknown matter that we call dark matter. Dark because we can't view it. And about the remaining 70% is unknown energy or dark energy, just because we can't perceive it. And these were postulated because the dark matter makes the galaxies spin at the rate that we see them spin at, instead of much slower. So there has to be like an extra mass in the galaxy. And dark energy was postulated because the expansion of the universe is not slowing down, but it's actually accelerating. And there has to be something that's countering gravity, that's allowing the universe to continue to expand. And that's what they postulated to be dark energy. Just going back to dark matter, although it's invisible, it exerts gravity just like visible matter. And so it served actually an essential role in our life by preventing the supernovae explosions and the matters that explode from them, by preventing them from dissipating completely out of the galaxy. And so it kept them in the galaxy, it kept them in the star systems. And so it allowed them to become the building blocks of planets, including Earth, including us. Now, these forces act using specific designated values. And those values are so extremely precise that any change, like any minute change in these forces or in other constants of the universe, will either lead to a universe that cannot harbor any star or planet. It will be just like a big pile of dust, or it will be like so condensed that it cannot even have planets or anything. It will be just like a big blob. So the values, the forces are extremely precise to allow the right ratio of matter to dark matter, the ratio of matter to antimatter, then the ratio of atoms, to enable the existence of stars, galaxies, planets, and life supporting Earth. And this is called the fine-tuning of the universe. Now, the integration of mass and energy is studied using various disciplines at various scales. So the interaction between matter and energy is studied by thermodynamics, which focuses on heat transfer and energy transfer, as well as electricity and nuclear physics. And the motion of matter is studied also at different scales. At the macroscopic or visible scale that we can see, it's studied by what we call classical mechanics or Newtonian mechanics and general relativity. And at the atomic and subatomic scale, it's studied by what we call quantum mechanics. And we will talk about each of those in the next slides. So let's talk about basically the interaction of energy and matter in the electromagnetic spectrum. So as you can see here on the left-hand side, I have an electromagnetic spectrum. So let's talk about this a little bit. So photons, for example, have different amounts of energy that they carry or that carry them. Because they behave like waves as they move, and they can only move, and they carry energy. The higher the energy they carry, the higher the frequency of the waves that they will adopt. And so only, and you see the spectrum here, only a small range of frequencies produce what we call visible light in red, written in red. Lower frequency photons become radio waves. And higher frequency ones, i.e. the ones with higher energy, contain, for example, gamma rays. And then above which there is cosmic rays that come from exploding supernovae from neighboring systems. Now, between these, there are other particles like high energy electrons or free neutrons that have higher energies and can penetrate atoms and they can cause what we call ionizing radiation, and we can talk about this when we talk about engineering. Now, regarding electromagnetism, the charged particles have a magnetic field, i.e., the electrons are basically like teeny tiny magnets, and those magnetic fields are carried by virtual photons, by the way. In most materials, these fields point to all directions and cancel each other out. But in magnets, these fields will be aligned and amplify each other, giving this kind of basically visible magnets. We talk about these kind of properties in engineering. So the next thing of interaction of matter and energy is heat transfer. So how does heat transfer happen? So when hot means basically atoms that are vibrating a lot, moving a lot, and bumping into each other. And so when those hot and bumpy and fast atoms collide with other atoms that are cooler, they will transfer kinetic energy, i.e. motion energy. And so this energy is basically heat. And so heat is transferred by molecules bumping into each other and transferring their energy. And it's actually mediated by the electromagnetic force, because atoms don't really touch each other because they're like magnets. And so they just kind of, just like you can see it as magnets repulsing each other, when a magnet gets too close to the other one, it's going to push it away. And so that's kind of the heat, how heat transfers. It is important as a principle of thermodynamics that energy in the form of heat or motion is constant in the universe. It cannot be created and it cannot be destroyed. Whatever happened in the Big Bang is what we still have. However, it can be transferred from one form to another, from one matter to another. And so this heat transfer is going to give us states of matter. So the energy makes atoms vibrate, accelerate, and collide, like we said, against each other. And that's called heat. The more energy, the more matter expands, and the less energy, the less movement, and the more matter condenses, until everything stops at a certain temperature that we call the absolute zero, which is minus 273 degrees Celsius. And matter exists in many states, from the coldest one called the Bose-Einstein condensate, to the solid form, to the liquid form, to the gas form, to the plasma, which is basically ionized gas, where like electrons are away from their nuclei, to the quark-gluon plasma, where all the internal constituents of the proton started to dissociate from them, which are called quarks. And that was actually the state of the very early universe right after the Big Bang, and it was about 4 billion degrees Celsius in heat. So now let's talk about the principles of motion. So we have two types of motion. We have the macroscopic motion, so it's studied by classical mechanics. So what does classical or Newtonian mechanics say in terms of principles? So objects move when a force is applied against them, and stop moving when subjected to an opposite force of the same magnitude. Therefore, the direction and the speed of motion of objects is the result of all forces acting on them, both in direction and in magnitude. So if we can see in this example, we have a rocket that's pulled to the ground by its own weight, the red arrow, and it's pulled away from the ground by the thrust. And because the thrust is exactly in the opposite direction of weight, they mostly cancel each other out, except that the thrust is more powerful. You can see the arrow is more powerful than that of the weight. So the resulting force is the force that proposes the rocket out into space. And obviously this is the simplified example because we have forces acting exactly against each other, but you can have forces acting on all directions, and some of them will cancel each other out, and the remaining one is the force where the object's going to be moving. Now, objects moving in a medium will be decelerated by the friction force. And what is the friction force? It's caused by the surrounding atoms of that medium that surround the object. And because the atoms of the object will bump against the atoms of the medium, they will transfer some of their energy as kinetic energy to those, i.e. transferring some of the heat out, i.e. losing some of the energy. And that's how friction reduces the speed or the power, the force of moving objects. Obviously, the denser the medium, the more friction and the more energy will be needed to push that object. Also, another principle of the classical mechanics is that the force that we're talking about, the force of motion, equals the mass of the object times its acceleration. And the mass is the sum of the mass of all the atoms that compose that object, and as such is constant. However, on Earth we speak about the weight, and the weight is basically the mass of that object multiplied by the gravitational acceleration, because he said force equals mass times acceleration. So the gravitational acceleration is what gives things their weight, which means that things have a different weight if they're put on different planets, and they will have no weight if they're in outer space. And so that's why it's important to differentiate between mass and weight. Now, all objects will attract other objects due to gravity, because we said gravity works in all potential directions. And so the more massive object will have more atoms, and so it will exert much more gravity on smaller objects than the opposite, and therefore attract them. However, it means that also small objects do attract massive objects. It's just that the force that they apply on them is much smaller. And so going back to the principle of applying the resulting forces, the resulting force is that massive objects will attract smaller objects much more than the opposite. The combination of these principles will allow us to predict and calculate the motion paths and the speeds of objects, be it on Earth like machinery or cars or boats or planes, or rockets that go into the atmosphere and outside, or even planets and galaxies. They all follow the same principles. Now, this is kind of an overview of the movement, in classical mechanics. Now, when we talk about larger distances like light years, there is another phenomenon that's going to start materialize, and that's explained by the Einstein's theory of relativity. So what does it say? So it suggests that space and time are part actually of the same fabric that was called space-time. And this fabric is warped by the gravity of the objects that are within it. Just like a piece of cloth where you put a ball or a heavy ball, the heavy ball is going to warp the piece of cloth. So you can see here in this illustration, a light beam is going to be bent around massive objects. And because we know that a light always takes the shortest path between any 2 points, this means that space-time itself is bending. This effect is very small and basically unnoticeable on small distances, i.e. like human scale distances, and only manifests at large cosmic scales, i.e. at light years. And you can see in this image taken by the Hubble's telescope, the lensing effect, what they call the lensing effect, which is the deformation and the lensing of the light of distant galaxies by two nearby galaxies, the ones that are very bright. And you can see the ones that are outside, they look bent, completely bent. And that's because of the curvature of space-time, because of the as evidenced by the described by the theory of relativity. Now, this is kind of at the visible scale how things move. How do they move at the atomic and subatomic scale? When we go to that scale, particles do not obey the laws of Newton, nor do they obey the laws of Einstein, but they follow other rules in what we call the quantum mechanics. Why is it called quantum mechanics? It's because those subatomic particles, they don't move in a continuous way, but they do like very small jumps, i.e. they disappear from one place and appear from a place right next to it. And those jumps, they're called quantum jumps. And that's why the mechanics that describes them is called quantum mechanics. So those particles can be actually at more than one spot at a time until measured, which means that those particles, instead of being at one place, they have actually a probability of presence. That probability of presence is going to be high in some areas, like for example the peaks that you see here, let's say for an electron or something. So the peaks are where you're going to expect to see it most of the time. But it will have a probability of presence that's very low in other areas, very low but not null, i.e. they can exist in those areas that are far away from what you expect them to be. So quantum mechanics is actually essential in all the electronic engineering, because without understanding quantum mechanics, it's impossible to create electronic circuits. There are two manifestations of quantum mechanics I just want to highlight. One of them is actually very important and the other is promising. So the one that's very important is what we call quantum tunneling. So what does quantum tunneling mean? Particles can basically appear outside of their highest probable position, like we said, obviously, albeit with a lower probability. And so it so happens that if you have two adjacent hydrogen atoms, let's say in the sun, for example, they're like so close to each other. Well, one proton, i.e. one nuclei of the adjacent hydrogen can basically tunnel into the other one. So basically disappear and appear inside the nucleus of the other hydrogen, and thereby cause nuclear fusion. So this nuclear fusion that's generated by quantum tunneling is actually the base of the functioning of the sun, and it's actually essential for the functioning of all stars and subsequently to our existence. The other concept that's kind of promising is quantum entanglement. And basically it says that if you have two particles that are paired, so basically they behave similarly, and then you separate them, if you change the state of one particle, it's going to immediately change the state of the second one. And this property is currently being researched to try to develop what we call quantum computers that are capable of simultaneous calculations and therefore much more powerful than traditional computers which operate linearly. And with that, we came to the end of our video on the principles of physics. Appreciate your comments and thank you for your viewing.